Okay, and then I think we really ought to finish programming and then moving on to the next topic. Okay, so I think we've finished that slide. So this just summarizes things that I've already said, that as part of a call, automatically, whatever's in the program counter gets put on the stack, and automatically, when you finish your little subroutine, you don't need to explicitly cause a pop. It's implicit in the ret that whatever's on the stack will be put back into the program counter. So this is just a warning to you that if you are using pushes and pops in your subroutine, you must have an equal number. Otherwise, you're going to leave something on the stack that's shouldn't be there, and when you do the ret, you're going to return to not when you thought you were going to return to, you're going to go somewhere else. But the big advantage of subroutines, as I already said, is it allows you to have a little block of code that can be referred to from elsewhere in your program many, many times, jumping into it to do some specific task, and then going back to where you came from. And you don't even need to remember where you came from because it will automatically be stored for you. Later on in this course, we'll be doing interrupts. And interrupts are like a very special form of subroutine, but they have their own version of ret. You can get back and on. There is this other version of call, a call, which allows you to go to a subroutine, but only a limited distance from where you are now. The subroutine has to be within the same 2K memory block as where you are currently in the program code. Now, some versions of the assembler will let you just use the word call without specifying L call or A call, and it will substitute in the right one for you. But that's assembler specific. Okay, as you might have started to notice from the Scott McKenzie book and some other things I've been saying, not all instructions take the same number of machine cycles to execute. That's because having fetched the opcode, some of them have to go and then fetch an operand or two operands and things like that. So different instructions require different numbers of machine cycles to execute. And if you have a program where timing matters, you can actually work out precisely how long it's going to take to execute any instruction. However, in order to get an absolute numeric value for the time, you need to know what speed your crystal is going. Because one machine cycle in the classic 8051 takes 12 clock cycles. Okay? So, for example, there's one here. So, in this particular case, if the clock frequency was 16 megahertz, then effectively one machine cycle would take 0.75, because it's a 12th of, the clock is going 12 times faster than one machine cycle. So one machine cycle, 0.75 microseconds, and then looking up in the instruction thing, you can work, you're told how many machine cycles different instructions take. Well, if you know what one machine cycle is, and for example, this instruction takes 2 machine cycles, it will take 2 lots of one machine cycle, 2 times 0.75 microseconds, i.e. 1.5 microseconds. If you are doing some kind of clock program, and you've carefully calculated all these times, and taken exactly the right amount of time, and you're all happy with it, bear in mind, if you change your crystal, you'll have to recalculate all those values. Because the machine cycles, the actual speed of those is directly related to the speed of your crystal. Right, now we're moving on to a block all to do with arithmetic with the 851. So the first arithmetic instruction we have, and we've met it before, is multiply. Multiply only ever works on registers A and B. So effectively, you multiply whatever's in A by B, doesn't matter which way around it is, but the result is stored such that the high value is in register B of the result, and the low value is register A. So for example, if we wanted to multiply 25 hex by 65 hex, we could store those two values in A and B, and then issue this instruction mul AB. That actually, someone's bothered to work out the result is E99. I'll take their word for it that that's correct. You would then find that B holds the high byte of the result, and A holds the low byte of the result, the 99. I think multiply is about the slowest instruction. And if you multiply and divide, I think they might take 4 machine cycles. The result, if you multiply two 8-bit numbers together, you can be sure the answer is going to be more than 8 bits. So that's okay. In the 8051, that's fine. It will store the upper 8 bits of the result in the B register and the lower 8 bits of the result in the A register. So when you multiply these two 8-bit numbers, the result could be a 16-bit number. Okay. Now you don't get to choose where which has got the high byte and the low byte. It's all Intel have decided that. So when you multiply them, the B register will always hold the high byte of the result, and the A register will always hold the low byte of the result. Division, that's possible as well. And the assumption is that the numerator, that's the top number in your division, has got to be in the A register, and the B register holds the denominator. If the B register, when you issue this instruction, div AB, contains the value 0, that's a divide by 0, effectively a flag, the overflow flag, will automatically be set for you to warn you you've just done something really silly. Okay. So the numerator's got to be in A, the denominator's got to be in B. You can then issue the instruction, and then you can see here that the quotient, the result goes into A, and the remainder goes into B at the end of that operation. And I think that's reasonably straightforward. Right, signed arithmetic. Generally speaking, in the 8051, when we're doing signed arithmetic, that's numbers where there's a kind of a plus minus in front of it. For representing negative numbers, we use two's complement notation. So, also, we use the most significant bit to represent the sign. A 0 in the most significant bit, we assume means that the result is positive, and a 1, we assume the result is negative. Later on we will see that if you're doing some signed arithmetic and you're adding two numbers, and as a result of adding those two numbers, the most significant bit changes value, a special flag will be set for you to indicate that actually the number got so big, it's gone into the sign bit and has actually changed the magnitude, which is bad. So, anyway, we're just adding two signed numbers here. So we've got 1 and we've got 5, and adding those together, and the result is fine. It's still 0, so that's okay. It means it's still a positive number. If we tried to add, sorry, this is just representing different numbers, so that's plus 1, 2, 7. Let me show you.
1 plus 5, 927.
Yeah, 2's complement. Let's blank this a minute. We want to do that. So, in 2's complement notation, remember which way around it is. Add 1 and invert, I'm not sure. Just check. Invert and add 1. And you would, in an exam, expect to know how to do signed arithmetic. So 2's complement notation of negative numbers. The way we deal with it is if you have a number let's say we have minus 7. Representing that in 2's complement notation is first of all already.
No, there's such an easy trick to that.
So
just make the most significant a minus, and then add the number.
one day I'll be able to remember this.
Minus 12. So add 4 to that.
So first of all, we take the number 7.
Okay, that's pretty easy.
And step 1, we invert it. Step 2, we add 1. So in order to represent minus 7, we start with the plus 7, do the inversion operation and add 1. And that's how we would represent the number minus 7. So for example, we could do plus 8 minus 7. We'll do that arithmetic. Okay. Effectively, this is the way we do subtraction, by the way, is a subtraction is just an adding of a negative number in sign arithmetic. So we'll perform this operation, but first of all we need to know how to represent the minus 7. So plus 7 is 0, 0, 0, 0, 0, 1, 1, 1. So that's plus 7. Then we're going to invert it. And then we've got to add 1 to the result. So that would be 2's complement notation for minus 7, I hope. Plus 8, thankfully, is easier. So that's going to be 0, 0, 0, 0, 1, 0, 0, 0. So that's the 8. So let's add these two numbers together. That's minus 7. So 1, 0, 0, 0. Carry 1.
You have to find
0,
first.
1, 0,
Before you
0,
add them
0.
together.
So the answer of 8 take away 7
Apparently not.
No.
is 1. It's plus 1 because the most significant bit is 0. So it's correctly done the operation for us, the subtraction.
How did that work if you didn't convert 8 into 2's complement? I mean,
You're converting the negative numbers to their 2's complement.
oh, not positive
Not
numbers.
positive
Okay.
numbers. If you did that to the 8, you'd be doing the minus 8.
Oh, okay.
And we're not doing that. We could do that, and then we can try it actually.
And it gives you the,
Just
gives
for
you
the
the
hell of
answer
it.
straight away.
So
No, it's just going to give you minus.
over here we'll do minus
minus
8
1, yeah.
and see what happens. So hopefully we'll get minus 15.
Okay.
Let's give it a try. So plus 8 is 0, 0, 0, 0, 1, 0, 0, 0. Then the first step is to invert it.
Oh yeah, you just added them
Check
together.
what it's doing. So that's the plus 8. That's the invert. And then we've got to add 1 to the result. So add 1 to the result would be, so adding 1 here. So 1 plus 1 is a 0, carry a 1, which becomes 2, so that's a 0, carry a 1, 2, that's 0, 1, 1, 1, 1, 1, 1. So apparently, that is 2's complement notation for minus 8. We'll then add that to the minus 7 and see what we get. Okay, so 1, 2, 3, 4, 1, 2, 3, 4, and then 3, 4, 1, 0, 0, 1. I think that's right. Okay, perform this addition. So that's 1, 0, 0, 0, 1, 1, 1, 1, I think.
Plus another one?
Have I got it wrong? Let me just check
Yeah,
again. So that's 1, 0, 0. That's a 0, carry a 1. So that's 1 plus 1 plus 1. So it's 1, carry 1. 1, 1, 2, 3, 1. So carry 1, 1, 2, 3, 1. 1, 2, 3, 1. I think that's all right.
But don't you have to carry the last one?
There is a carry out, that's true. Yeah.
So you just ignore it.
But we ignore that. So we end up with, have I got this right? Yeah. The reason why, of course, the result, let me see.
You can do that. Wait,
You have to
one,
invert
two.
that.
That's what I'm just
No, you
thinking.
won't.
1, 2, 4.
No, you won't. You go minus 15.
I don't know. Let me just check.
So wait, 1, 2, 4, 8.
Yeah, because it's now it's.
I've got one I did earlier.
So you have to choose complement again. I shouldn't have asked that question.
No, but that should be minus 15 though, on its own, in 2's complement, right? So it's 1, 2, 4, 8, 16. He's got 32, 64, and 128. Damn! Why would you go so far? Oh, you can still do it like that. 1. Yeah, it is. Yeah, it is. It's minus
It's right,
15.
is it?
Yeah, it's right. It's right.
What happens to the carry out?
Oh, overflow. Ignore it.
So, but how do you get them?
Oh no, you can still add it. You can still add it.
Okay.
You can still have a 1 there. Because if that was 256, add 128, add 64, add 32, add 16, add 1, minus 15.
Yeah. Awesome.
Somewhere in here I've got 2 negative numbers.
Seriously, my trick just works.
Yeah, that's what wicked trick. Did you work it out or did someone teach that?
Yeah, no. You see it. You see it. Like the first time I learned it in college, I just saw
That's
it.
right, so
It's good.
I remember trying to teach it to Robin in a lecture, in math and maths lecture, because he just looked dumbfounded. So I don't get this. I don't get this.
It's one of those tricks you need to
I know why,
Thinking.
because that is the correct
I need to
result.
work out what that is.
But
That thing
it's a
about being
negative
stubborn,
number, but we
looking
want to
for
know
one
what
such
the
a-
value of that negative number is. So now we've got to invert the 2's complement. Basically the result.
If you could channel that.
The negative
thought
numbers,
process
they're
right,
represented in 2's complement notation.
And
So
it's completely okay.
this may well be
People think
correct.
I'm
What I haven't done,
so you're just-
we're looking at this
Headsets,
number
yeah.
and just treating it just like an ordinary number. But because it's a negative number, our negative number representation is 2's complement notation. We've got to say, well, what's the magnitude of this 2's complement number? So we've got to do the inverse of what we did to do the 2's complement to see if we've got the correct magnitude. Okay? So, let me try that.
Let's go.
So this number will assume, because it's negative, it's a 2's complement representation of the number. So we know it's negative, but we now want to know, well, what's the magnitude of this negative number? So we've got to do the opposite of what we did to make it 2's complement. So to make it 2's complement, we inversed and added 1. So we're going to have to subtract 1 and then invert. And that will then give us the correct magnitude. So we're going to subtract 1 from this number. So take away 1 from that will give us the first step of, we're doing the reverse of the 2's complement, which will be step 1. We then have to invert the result.
Or you could invert and then add 1.
And the result is 15, which is correct. Minus 7 minus 8 is minus 15. Because it's a negative number result, the result is effectively a 2's complement representation of the number. So what we wrote here was, which one was the result? Was that the result? Well, that was the result, wasn't it? I can't remember which one. This result was correct. But it's hard to look at and actually just look at it and say, oh, well, that means this number. Because this is a 2's complement representation. Because it's a negative number. But if we want to know the magnitude of this negative number, the only way we can do it is the reverse. Yeah?
You can still work out what the value is by using the, if you put the powers of each column,
Yeah.
and the last one
Yeah.
is minus power,
Yes, I think you're probably right.
Yeah.
work out that way.
Yeah. You're probably right.
Yeah, it works.
Yeah, it works.
Okay.
It works. That's what I've been doing.
Okay, good. All right, if you have a better way of doing that, that's fine. But anyway, we've just done it, if you like, simple reverse engineering of what we did when we, to basically, to represent a negative number, from a magnitude. We've just done the opposite thing. That given a particular number, we just want to get the magnitude.
Now we do not have to see the sign bit.
The most significant bit here was, it did matter. Now you might say, well, how do I know if I'm doing addition or subtraction? Because you explicitly call the instruction whether you're doing subtraction or addition. If you're doing subtraction, it will effectively do the 2's complement of the second number automatically. So you'll find that in the 8051 there's add with carry, I think, or there's also add, and there's a subtract. In the instruction, if it's an add, it's basically just going to add 2 numbers. If you do a subtract, it will automatically convert the second number into the 2's complement notation, and then add it. So a subtraction is really an addition, but where one of the numbers has been converted into, has been effectively turned into a minus representation. Now it could be a negative number to start with, in which case it would make it a kind of positive thing, you see what I mean? So if you did, I don't know, you had a signed number like -7, -5, and then you called up the add, it would just add those 2 numbers. If you do a sub, in order to achieve that, it would take the second number and do the 2's complement of the second number, and then perform the addition, which I imagine will give you a result of -2, because you're minusing 5.
That's still working.
So, anyway, here's some other examples. So in order to represent a negative number, we start off with the magnitude of the number,
Yeah.
and then we invert it and add 1 to give us the 2's complement notation for the negative number. For a positive number, we don't go through this step. So if you have a +6, a +6 is a +6 and that's it. If you have a -6, we perform this conversion in order to represent the minus number in 2's complement notation. So there's an example here where we're actually effectively doing a subtraction. +8 -6. The +8 is a positive number as it is, so it just stays as it is. We don't do the 2's complement of that number. But because of the negative here, we're basically, you can either think of it as adding a negative number or subtracting a number or whatever. This number has to be represented as 2's complement notation. We started with the magnitude of +6, inverted, and then added 1. And then we can add these 2 things together, and we end up with our result. Our result is a positive number, because there's a 0 here, and its value, its magnitude is 2. If we ended up something where this was a 1, it means that we've got a negative result. To actually work out what the magnitude of that negative result is, we're going to have to use a technique, either like the one I did or the one you did with the negative power, in order to work out what the magnitude of the result is. You would be expected to know about 2's complement notation for negative numbers in this course. So, how to represent a number, a negative number, as its 2's complement. Next little bit of arithmetic. Binary coded decimal arithmetic. Okay? So for binary coded decimal arithmetic, you're adding numbers, but the numbers that you're adding, it's not permitted to have a number in a column that's greater than 9. You know, you've got your, in decimal, you've got your units, your tens and your hundreds, you know, remember primary school. Obviously, if we're dealing with kind of hexadecimal, it's permitted to have values like A, B, C, and so on. Well, that doesn't make any sense if we're doing decimal arithmetic. in order to help you, if you wish to do decimal arithmetic in the 8051, you can just do your normal additions as you would, but if you don't do anything about it, there are going to be occasions where you would get the wrong result if you didn't make adjustments. And here's an example where we have two numbers, for example, in decimal that we wish to add. So 59 added to 38, which apparently is 97 decimal. Okay? Let's convert those to their binary equivalents, and let's just add them up. So if we ask the 8051 to just add these two numbers, we'd end up with this result. This result has the value 91. Well, 91 is not the right answer if you were adding two decimal numbers. So we can cope with that. There is a special instruction that allows us to adjust the result to take into account that we're dealing with decimal numbers as opposed to hexadecimal numbers, if you like. And this is this special instruction called decimal accumulator adjust, DAA. Sometimes we just see it written DA. And it actually does a whole host of things. It's quite a complex instruction. One of the things it looks for is whether there's been a carry from this nibble into this nibble. If there's a carry from the lower nibble into the higher nibble, it will automatically add 6 to the value that's in the lower nibble. So that's one thing that it does. And in this particular case, you can see that this would have been a useful thing to do, because this result, we add 6 to it, 1 plus 6 is 7, we would end up with 97, the correct result. So when you call this decimal adjust, we basically can convert the result so that it's appropriate. So if there's been a carry from one to the other, we're dealing with base 16 here, effectively if there's been a carry here, then we need to take into account there's 6 more units there should have been than there were, so to speak, so we have to add 6 to the lower nibble. So what you need to remember is this decimal accumulator adjust. One of the things it does is if there's a carry from bit 3 to bit 4, you must add 6 to the result of the lower nibble. That's one thing. If there's a carry out, the same thing applies to the upper nibble. Now you might say, well, there's a carry here, but there could be a carry here too. It's okay, because there are actually, in the 8051, 2 carry flags. There's the normal carry that we've been fiddling around with, which is from bit 7 outwards. There's something else called the auxiliary carry, AC, that deals with carries that go from bit 3 to bit 4. Now, when you're doing your additions and things like that, that carry flag may or may not be set lots of times. And most of the time, you just ignore it. It doesn't matter. But if you want to do a decimal adjust, the special instruction DA will actually look at that auxiliary carry flag. So let me go on to the next slide. And then, this is just going into more detail about that. So because there's been a carry from bit 3 to bit 4, we've added an extra 6 to the result, which is now corrected for the error, so to speak. But like I say, it is more complicated than that, because you can see here. So if there's a carry between the 2 nibbles, the auxiliary carry flag will be set, and that will cause us to add 6 to the result of the lower nibble. But also, where is it? I'm just checking here because there's another part to it. You might end up doing an addition where the result in here is a value that doesn't cause a carry from there to there, but is a value that's in the range sort of A, B, C, D, and you have to adjust for that too. So, try and think of an example. So,